Good morning. We will continue our discussion. So, last day we have seen that what is the small signal analysis of common source stage with source degeneration. So, if you consider the T model, so what is CS stage? This is our output, this is VDD, this is RD and ID current flows, right, and this current is also equal to ID because ID is equal to IS. Now, we can replace this with T model, and what we will do, we will consider this is as AC ground and we will draw the circuit. So, this is 1 by GM, right, and our Ig is equal to 0 and this is GM VGS, right, and we have extra resistance RS to the ground and say this is V in, and from this resistance RD is grounded. So, you see this output is I into RD, and what is I, that we will have to find out, clear. So, this V0 is equal to, suppose I current is flowing through this, so minus I should flow this, right, and same I should flow through this, okay. So, V0 is equal to minus I into RD, that we know, clear, and from this we have to calculate the I. What is the total resistance? 1 by GM plus RS. So, V in by 1 by GM plus RS, clear. So, what is our V0? V0 is equal to minus V in RD by 1 by GM plus RS. If you rearrange this, multiply with GM, what it becomes? Minus GM RD V in by 1 plus GM RS. So, what is your AV now? V0 by V in is equal to. So, can you solve that now? Clear? So, what we are doing? We just replace this BJT, this MOS with our T model, clear, and what extra we are doing? We are considering that VDD is grounded, AC grounded, this is AC small signal analysis, okay. So, I have described this yesterday and today we also derive the expression, so that I am repeating so that you get familiar with all of this and you can do this confidently. Okay. Next is our 3 MOSFET configuration. So, 3 configuration we all know, one is common source that we just have studied, another is common drain and another is common gate, right. So, what you know about common source? Its gain is roughly GMRD, right. So, it has a 180 degree out of phase relationship, and what is the input impedance of common source stage? Infinite. What is the output impedance of common source stage? Moderate to large, right. Why? Because it is R naught. Similarly, we will see what are the characteristics of. So, these are characteristics, right. This gain is this much, input output phase is in out of phase, okay. Input impedance is high, output impedance is. So, these all are characteristics of each of these amplifier that you have to be familiar with. Another thing is application where you can use it, right. So, common source you can use as an amplifier, but still it is not, input output relations are not suitable, right. What is input impedance and output impedance requirement of a voltage amplifier? R in should be infinite, R out should be 0. So, is it matching with common source? Although common source is giving me a gain, but is this output impedance matching? No. So, you cannot make this as a full amplifier, but it can be used as an intermediate block, right. You have seen that several stage of amplifier can be cascaded, right, to make a large gain amplifier, right. So, in somewhere in between I can use this common source as a block, because input impedance is matching. So, maybe I can use in first stage or second stage, but output stage what it should have and input stage what it should have. In between I can have a buffer or something like that, right. So, this matching, this impedance requirement, you should be clear that if I have an amplifier, this is my requirement. If this is a voltage amplifier, what is your requirement? If it is a current amplifier, what is your requirement? But voltage and current, they are just complementary, right. So, that you can remember and other you can calculate. So, let us just quickly recapitulate this common drain stage. So, common drain stage, it can behave like a buffer, and we have seen that suppose V in is 0. So, no current flows. So, I is equal to 0. So, this V out is equal to 0. So, it starts from 0. So, after what it starts building up current? After Vt, right. So, it is like a phase shift, this DC shifted, this is a DC shifted, right. So, input and output, they are nearly same, nearly following, but this output is input minus. Okay. Next is how to find the small signal analysis. So, for example, in this case, if we do the replace this MOS with its small signal model. So, this circuit or this circuit, this is a with hybrid pi network, this you can also do, this is a T model. So, let us assume with T model. So, you see here Ig is equal to 0. So, your V sig is equal to Vi, right, no drop across R sig. So, if it is, if this node is Vi, then I can get this node. Why? Because this is just a potential divider. So, this is my Rs, this is my 1 by Gm, and this is my V in or V sig, whatever you say. So, this voltage is my output now. I am taking output from the source terminal, right. So, my V 0 is equal to Rs by 1 by Gm plus Rs into V is equal to Gm Rs by 1 plus Gm Rs, right. So, if we roughly neglect that Gm Rs is much larger than 1, so it will become close to 1, gain is close to 1, but it is less than 1, gain is very close to 1. Okay. So, this is our expression. You can term this as RL, or you can also term this as Rs, both are okay. It is, you are taking output from this source resistance. So, you can, in one book they have termed as RL, load resistance, in other book as it is connected to the source they have termed it as Rs, but the expression remains same, Gm Rs by 1 plus Gm Rs. Now, extra one GMB term is added because this is called backgate effect. The source voltage is modifying the threshold voltage. As a result, what will happen? Your current will vary. This effect is modeled by backgate transconductance GMB. So, what is the meaning? If VTH is varying, my I will also vary, plus or minus. So, this is modeled by a transconductance into, it depends on which voltage? Bulk to source. So, this current source is modeled by the variation in the threshold that will change your current, and that is modeled by this extra. So, what is the, if you consider this back gate, what is happening? Your gain is little bit more decreased, okay. And you can consider both back gate or without back gate, just like we consider lambda effect and R0 we consider or do not consider, same way. So, these are all non-idealities, okay. These are non-ideal effect. Ideal MOSFET, we have a straight current characteristics. If we consider the lambda effect, then it get a slope, right. So, same way these are all non-ideal effect. So, we discussed what should be our small signal gain of common drain stage, right. Next, can you tell me what is my input impedance of common drain stage? It is connected to gate. Any current, gate current flows? No. So, R in is infinite. Now, I am looking through the source terminal. What is the resistance? 1 by Gm. This is large or small? Small. What is gain? So, this can be behave like a unity gain buffer. So, this is one application. So, this also we discussed. So, for this case, what should be our V0? RL by R sig plus RL into V sig. What is the value of RL? 1 K. R sig 1 meg means 10 to the power 3 K plus 1 K into 1 volt. If you roughly neglect that, 1 is neglected. So, this becomes, what was our target to deliver, and what we, our target was to deliver 1 volt, and now we are delivering 1 millivolt. So, what do you think, where is the problem? Who is the problem? Who is creating the problem? This resistance is quite high. So, to deliver output voltage, I have to deliver a current. So, drop is happening across these, and that is a, this is a subtraction, right. So, I have two solutions. One solution is that my load resistance should be comparably higher, so that, or this ratio should be balanced, right. Now, this is not happening, but still my requirement is that I should deliver 1 volt. What I can do? This portion is fixed, I cannot change. This portion is fixed, I cannot change. So, I cannot connect them directly, that I understood. So, what can I do? I can take a amplifier whose gain is 1. So, gain is not important, but what it is doing? It is giving a very large input impedance, so that no current flows. So, if no current flows, no drop is in here, right, and output impedance is 0, again at output side due to this amplifier no voltage drop. So, whatever the amplification voltage, this input voltage will come to the output. So, it will become better, right. So, what we will do? We will replace this with A, and here we should have a infinite resistance or a R in, and this is our R sig. Now, this is a potential divider, you can get this voltage, and this Vi should be this Vi. So, first what you will do? You should calculate this Vi using potential divider. Next, this voltage will come here, because this gain is 1. Now, this Vi and this 2 is again potential divider. So, you can get this voltage. Clear? Can you do this? Okay. If you do this, then you will see that now my output voltage is improved to 0.9 volt. Okay. So, you understand when there is an amplifier, if we use the two port network, then it is easier to solve, right. It is like just become a potential divider, just like this equation, this form. Okay. So, try this kind of problem, and you should understand that what is the meaning, why this drop and how this buffer can improve. Common gate amplifier. So, this gain, it should be again minus I into R d. This gain is V 0 is equal to minus I into R d, right, and I is equal to minus G m V sig. So, this V 0 will become G m R d V sig. So, V 0 by V sig, which is my A V 0 is equal to G m R d. You see, this is similar to my common source. In common source, my V sig was here. So, it was like V G S was V sig minus 0 is equal to V sig, but in this case gate is 0. So, my V G S is 0 minus of V sig is equal to minus V sig. Okay. So, current is minus I into R d, voltage minus I into R d, and I is again minus G m into V sig. So, this twice minus na. So, this gain is positive. Understood what I am trying to say? You see, I current is flowing through this, not I, minus I. So, what is this output voltage? Minus I into R d, just Ohm's law, nothing else. V is equal to I R. So, V 0 is equal to minus I into R d. Why this is minus I? Because of KCL, right. I current flows through this. So, in the opposite branch minus I current flows through this, so that the sum of all the current at any node is 0. Clear. So, only difference with common source was that in common source my VGS was V sig, because signal was given at gate voltage. Now, I am giving the signal at the source voltage and gate is AC grounded, may not be in complete circuit, may not be ground, because I still need to give a VGS above VTH, right, to turn this on. So, this ground, do not get confused that gate is grounded, this is for the AC circuit. You see, one DC voltage is there, but if I do this AC analysis, what I should consider? All the DC sources are sorted to ground. Understood? So, if in any circuit it is shown that gate is grounded, do not understood that gate is ground, this is AC ground, but unless you give a bias, this transistor will not turn on, and if it is not turned on, you will not get a output, right, it will be constant. Clear? So, this concept is clear. So, now tell me, if this BJT, this MOSFET is off, what will be my output? If suppose this is off, my ID is equal to 0, what should be my output? Output should be VDD. So, generally you may think, if it was the previous case, your ID is 0, output should be 0, because I am taking from the lower terminal. So, this drop is positive, and if this is 0, this node should be also 0, because no current is flowing. But in this case, I am taking from the drain terminal. So, if no current flows, this is VDD, so this should be also VDD. If no current flows, two terminal are having at same potential. So, if this is at VDD, it should be also at VDD, but if this is at ground, this should be also ground. So, be careful that what is the circuit connection. Previous case no current was flowing, output was 0, but in this case no current is flowing, output is VDD. Getting my point? So, these things, seeing the circuit you will understand. Okay. Do not just blindly assume that okay, previous case no current flows, it was 0, but here the circuit is different. Okay. Okay, done. So, if no current flows, my output is VDD. So, can you tell me when this MOSFET will go off, input low or input high? If input is low, it is getting it VGS. My input is at the source terminal, VG minus Vs. So, if your input is high, then your when this source Vs, when Vs is maximum, VGS is minimum and it may be 0. Okay. So, again do not take it, in previous case it was different, now it is different, because previous case my source was at gate. So, if input is increasing, VGS was increasing, but in this case if input is increasing, VGS is decreasing, because it is at source and it is subtracted, right. So, when V in is 0, I am getting, when V in is equal to 0, how much VGS I am getting? Total VB. If V in is 0, whatever the gate voltage, that is my VGS, right. So, what happened to the current that case? I is maximum or minimum? Maximum VGS, this is max. So, current should also max. Now, what should be output, maximum or minimum? Minimum. Why? Because V out is equal to VDD minus IDRD. So, if current is maximum, this subtraction is also maximum. So, that is my plot. When input is 0, what is my output? You see VDS sat, it is at the VDS saturation. What is VDS saturation? VDS saturation is equal to VGS minus VT, V overdrive voltage. So, it start with VDS sat, V overdrive voltage, and it's as my input is increasing, current is reducing, output is also increasing, and when it cross this VB minus VTH, means just less than VTH it will get, it will go, no current flows, output will go to clamp to VDD. Clear? So, do not just blindly believe, you try to analyze what is happening. Okay, it is starting from 0, what is happening, when it can go off. So, 3 region you just remember, at linear what is happening, at saturation what is happening, what is the point of saturation, and when it is off what is happening. Okay. So, you think of when my I is equal to 0, what is happening, when my I is max, what is happening, output is increase or decrease, and when my current is minimum, what should be my output. So, these 3 questions you should ask yourself, then you can calculate the values. So, let us just discuss the input and output impedance of this. Input is taken at which node? Input is taken at which node? Source node. What is the impedance? 1 by GM, high or low? Low. Output is taken at, what is that? R naught, high or low? So, this can match with which amplifier? Low input impedance, high output impedance, current amplifier, right. So, the input output is matching with the requirement of current amplifier, or it can be, you can use that as an intermediate block of a gain stage. Okay. And what is my gain expression? AV is equal to GMRD. Okay. So, let us compare. Common source stage input impedance infinite. Why? Input is given to the gate, no gate current. Gain minus GMRD. So, phase relation between input and output, in phase or out of phase? Out of phase. If I have an output load resistance RD, my output impedance will be R naught parallel RD, or sometimes if we neglect R naught, it is RD. If we consider another load resistance RL, then this is GM RD parallel RL. Okay. Next is with RS degeneration. What will happen? GM RD by 1 plus GM RS, rest of the things we are same. Common gate input impedance, we just see 1 by GM. Gain expression still same, GM RD, only minus sign is not there. Okay. And if I have another extra resistance RL, GM RD parallel RL. Source follower or common drain, input impedance infinite because it is giving to the gate, AV nearly 1, output impedance 1 by GM. Okay. So, this two you remember, when we look through the source terminal we see 1 by GM. Okay. So, this is a summary of characteristics. So, source configuration is best suited for realizing the bulk of the gain required in an amplifier. So, it can be used as an intermediate gain block, okay, intermediate voltage gain block, either a single stage or a cascade of 2 or 3 stage can be used. So, this CS stage, it can be used as a single stage amplifier or in a intermediate block of a cascade amplifier. If we include RS, what will happen? The dependence on GM will reduce. Gain is reducing, but my dependence on GM is also reducing. How? GM RD by 1 plus GM RS. If we neglect 1, so this is GM RS, RD by RS. So, dependency on GM is getting reduced. Is it good or bad? It is good because we have no control over GM, it can vary, and if it is varying, your gain is also varying, you have no control. You have designed an amplifier and you want it gain to be fixed, but it is changing all the time. In your lab you can do the experiment, it get it heated up, you have gain of 6, suddenly it becomes gain of 5, your sine wave is fluctuating, sometimes it is giving more gain, sometimes it is giving, so you have no control and you do not want that. The low input resistance of the common gate amplifier make it useful only in specific applications. Okay. It can be used in high frequency, better high frequency amplifier, or sometimes it can be used as a part of a current amplifier also. The source follower or common drain, it finds application as a voltage buffer. We discussed voltage buffer in case you need a impedance matching, a high resistance source to a low resistance load. Also it can be used in a multi-stage amplifier as an intermediate block or a buffer block. Clear? So, these are the applications where you can use it. Biasing, is this important? This is required or not required? You are doing the laboratory classes, right? If you do not do this biasing, your circuit will work? No. So, this is the first step. Which kind of biasing is this? Potential divider. Okay. We discussed about different biasing technique now. So, I am not repeating those, you can follow the old class. Okay. How many different biasing technique are there? What is this? Coupling capacitor. Purpose? To connect the AC signal, but not to disturb the DC biasing. Okay. Rest of the things are same. Now, next is frequency response of an amplifier. We have two terms, one is bandwidth, okay, and another is cutoff frequency. So, suppose this is my band pass filter. What is this? Band pass. Why? Because it is blocking the low, also blocking the high. It is passing only a band of frequency. So, if I ask you what is the bandwidth of this amplifier, what you should say? This is called lower cutoff and this is called higher cutoff frequency. And which point should we consider? Suppose this is my A. So, where it is followed by, say it is A dB, and where it is falling by 3 dB, that point I will consider as a cutoff frequency. So, the frequency difference between this lower cutoff and higher cutoff is known as bandwidth. Bandwidth means where the gain is almost flat, constant. So, if it is something like this, what is my bandwidth? From 0 to cutoff or say higher cutoff. You can say also corner frequency. So, this bandwidth is equal to Fc minus 0 is equal to Fc. So, this bandwidth is equal to Fh minus Fl. So, what is bandwidth? Where my gain is almost constant or flat, clear. So, one definition is covered. Next is corner frequency. What is corner frequency? Where my flat gain or the maximum gain, that is fall by a 3 dB, is known as the corner frequency. What is this slope? Roll off. If it is a one pole system, it is a minus 20 dB per decade. Okay. What is the meaning of this 20 dB per decade? What is the meaning? Decade means what? 10 of what? Frequency. So, what is the meaning? If my frequency is changing by 10 times, say Fh, say 10 Fh, how much gain will fall? 20 dB gain will fall. So, this slope is 20 dB per 10 times frequency, clear. If I term it as a octave, octave means this is 6 dB, right, 6 dB per, this is 20 dB per decade, and in case of octave, octave means twice the frequency, okay. That times it falls by 6 dB per decade, 6 dB per octave. I will check it and I will confirm, okay. We have discussed this before also, right. Okay. So, this is my lower cutoff frequency, this is my higher cutoff frequency, and this is my bandwidth. So, any amplifier, they by nature they can behave like a band pass filter. Okay. So, we have a higher cutoff and it is 1 by RC, right, time constant is roughly 1 by RC. So, if I want to have high frequency cutoff, this RC value should be large or small? This should be, I want inverse of this is large. So, RC value should be small. If I want a lower cutoff, what is my RC value? Should be large. So, this coupling capacitor, this is large or small? Generally large value. This, okay, this your looking in resistance is also large, right. So, this will give which cutoff? This will give a lower cutoff frequency. So, this bandwidth, this is due to this cap. Okay. Similarly, at the output, this MOSFET will have its internal capacitance, and internal capacitance are very small in values. We calculated the total C of COX, and how was the range of that capacitance value? We calculated, it was in femtofarad. Femto means, so if you take a inverse of that, which frequency side it will go? So, this is due to the internal cap. Internal cap means suppose this wire is having some cap, this drain to bulk is having some cap, right, parasitic capacitances. Drain junction with the bulk junction they will form a capacitance, drain junction with the gate will form a capacitance. So, all of these are known as the internal capacitance and they are of very small value. So, if you take inverse of that, that will be responsible for the higher cutoff. Getting my point? So, if any frequency is falling, that means some impedance is changing, right. So, which impedance is frequency dependent? J omega c. The impedance of the capacitance is dependent on frequency. So, if frequency is varying, its impedance is also varying. So, whenever any fall is happening, that means some RC component is responsible, and if it is of large value, it should give a lower cutoff. If it is of a very small value, it should give a higher cutoff. Clear? This is body effect. We discussed this, that if we see the threshold voltage, we have an dependency on the source to bulk voltage. Okay. Our threshold voltage depends on the source to bulk voltage. So, if source to bulk voltage is changing, my threshold voltage will also change. So, one coefficient is taken as gamma, which is called the backgate coefficient, that we modeled with this GMB. No? GMB is an effect of this backgate effect. So, what is backgate effect? If we change the source voltage, that source voltage affects the threshold voltage, it changes the threshold voltage. So, this effect is known as the body effect or backgate effect. Now, this MOSFET that we have studied, this is known as the enhancement type MOSFET. By default, it is enhancement type MOSFET. So, we generally do not use a enhancement type MOSFET, we just tell it MOSFET, but it is a enhancement type. We need to enhance the gate voltage so that it can work. We need to enhance the gate voltage so that it goes above VTH and you get a channel current. Okay, clear? So, enhancement MOSFET is normal MOSFET. We need to enhance the gate voltage above threshold voltage so that I get a drain current or channel current. Symbol, generally we use this symbol, NMOS symbol, and PMOS symbol is the source is higher side, source is at higher potential. In NMOS, source is at lower potential. In PMOS, it will be just opposite, source is at higher potential. So, you check the direction of arrow. Okay. This direction of arrow is from source to the channel, this direction is channel to the source. Why? Our electron is flowing from source to drain, but direction of current is from drain to source. And here our majority is holes, right. Here channel is, when channel is inverted, electron is taking part in carrying the current, right. Here holes will take part in carrying the current. So, if we want to think like a digital circuit, in NMOS, when gate is, which logic it should turn on, 0 or 1? VGS should be high, na? So, gate should be 1, then it should turn on. In this case, source is at, suppose at VDD, VDD means logic 1. So, if I give 1 at gate, VGS is equal to 0. So, it will turn on at which volt logic? 0. You see, I need a high VGS. So, if I give a 1 at gate, it will be on. If I get a 0 at gate, it should be off, because VGS is 0. In PMOS it will be just opposite. If I give a 0, it should be on. If I give a 1, it should be off. Clear? To turn this on, my gate should be high. To turn this on, my gate should be, why? Because source is at VDD, here source is at ground. Okay. So, source is already VDD. If you make VGG also at VDD, so what is mod of VGS? Here source is at 0, if you get gate also 0, what is your VGS? 0. So, it turns off at 0, it turns off at 1. Next is depletion type MOSFET. This is a special type of MOSFET where a channel is already depleted, a channel already exists. So, even at 0 gate voltage it will carry a current because channel exists. Okay. A channel already depleted, so even at 0 gate voltage you get a current. Now, if we want to turn it off, we have to provide a negative gate voltage. Understood? Previous case we need to provide a positive gate voltage, enhance positive gate voltage so that it is above VTH to carry a current. Here it is already there. So, symbol is like this, a thick, okay, this depletion. So, this is the symbol, and if we want to see the ID versus VGS, even at 0 VGS it flows a current, and if I want to turn it off I need to give a minus voltage. Clear? What is the difference between enhancement and depletion? Enhancement was like this, at VTH it was turning on, this is ID, this is VGS. What is ID versus VDS? ID versus VDS, it looks like, okay. Be careful about these two plot, this axis is changed, okay. This is input characteristic, this is output characteristics. So, this is my enhancement, and difference of depletion as if left shifted.